But if you're gonna start a rumble, don't you try it all alone, because I'm evil.
We talked about using algebraic methods to arrange our equilibrium constant, using our equilibrium constant where we can arrange some form so that we can solve it algebraically, where we have this change that we can represent as a variable and use algebra or the quadratic, something like the quadratic equation, to solve for x, solve for the change. Right? Anytime we can arrange it so that there's only one variable, this allows us to get to a solution. The trouble is this takes a long time. All right? Though we do have simpler simplifications, and one of those simplifications is the perfect square, which when we have the general form, a minus x, or something along those lines, all divided by something along these, we can take a square root of both sides, and when we have this perfect square, this can be simplified, or something along those. Now the last one, and probably the most useful simplification, is to use information in K. When K is very, very big, or K is very, very small, there's some implied information that deals with the relative size of K and the amount of the shift in the equilibrium. And so this is where we use our assumptions, simplifying assumptions. So let's take a look at an example of this. Turns out that water at 25 degrees C is in equilibrium with H2 gas plus O2 gas. These are all gases at this particular temperature. And it turns out that water actually will split naturally into hydrogen and oxygen. Yay, we've solved the energy crisis. Oh, except for the little simple fact that Kp for this equilibrium at 25 degrees is equal to 2 times 10 to the negative 42. All right. And if you've been paying attention, you know that what this means is that the products are not favored in this reaction, and the reaction almost solely lies towards the starting materials. We can write the form of the equilibrium constant such that Kp is equal to the partial pressure of H2 squared, and the partial pressure of oxygen, all divided by the partial pressure of H2O squared. Now, we can use the initial concentration. If we knew that, say, the initial concentration of water vapor at 25 degrees, the initial partial pressure, 25 degrees, was 0.05 atmospheres, we know that the change at equilibrium, the amount lost, would be minus 2x, and thereby the amount gained would be plus 2x for the hydrogen and plus x for the oxygen. And we could plug those values in, all of the values in, to give us 2 times 10 to the negative 42nd is equal to 2x squared x and 0.05 minus 2x squared. And we could use the quadratic equation to solve this. Or actually, this would technically be a cube term, and you'd be left with all sorts of fun algebra to massage this. And so maybe actually we should write that. Right? But instead, there's a simplifying way. Right? If we look at this equilibrium constant, what we see is that we've just said that this reaction really heavily favors the starting materials. So what does that tell us about the relative magnitude of x? X, the change, that's what it represents, the amount consumed, is going to be small. What that means is that if x is small, 0.05 ATMs minus 2x will approximately equal 0.05 ATM. As long as x is really small, this will be true. Right? It's the loaf of bread example. Bill Gates goes to the grocery store and buys a loaf of bread. He's still got $1 million. Okay? So it doesn't really matter how big that value is. As long as x is small compared to the amount we're subtracting it from, it is still small. And so it's effectively unchanged. So we make the assumption. The assumption is that 0.5 ATMs minus x will equal 0.5 ATMs, and so we can then plop that back into this equation, and we get the following. 2 times 10 to the negative 42nd is equal to 2x squared times x, all divided by 0.05 ATMs. What this does is it eliminates this square term from the bottom and greatly simplifies our math. This can be rearranged and simplified to the following. Which means that we can very easily rearrange and solve for x. So if we do this, it turns out that x would equal 3 times 10 to the minus 15th atmospheres. Knowing that, we can look at our assumption and say that yes, our assumption is valid. Whenever you use your assumption, whenever you use these assumptions, you have to check it. If you don't check it, the answers will not. You have to check to make sure that x is suitably small compared to the value that you're in the assumption. Right? Usually we're looking for about a 5% or so difference in the value, and that we can assume the value is valid. So roughly, I like to err on the side of about 1% to be even better. But as long as it's a 2 or 3 orders of magnitude difference, you're usually golden. So where this is useful is when k is very, very large, or when k is very, very small. And by very, very small, we're looking 10 to the third, 10 to the negative third, or so. All right, those kind of ranges, and then it's effectively, in those ranges, then the equilibrium constant values are sufficient that the change is predominantly one side or the other. We will use this example over and over and over again when we get to acids and bases. So this assumption is very powerful for us. Now, again, I did the cardinal sin. I didn't actually answer the problem. What are the partial pressures of H2 and O2? Well, in this case, the partial pressure of H2 should be equal to 2x, or in this case 6 times 10 to the minus 15 ATM. Partial pressure of O2 should be equal to 3 times 10 to the minus 15th ATM, and the partial pressure of water would be effectively what it started at, 0.05 ATM. And if you plug those in and you check, you get a value that's pretty close. You plug those in, you get a value that's pretty close to 2 times 10 to the minus 14th, 2 times 10 to the minus 42nd. You get a value that's very close to that, which shows that our our assumption is valid.